Hi, everyone, and welcome to my workshop preview, the Jumpstart Guide to C++ in Audio. Who am I? My name is Wilczek, and I'm an audio programming consultant and coach, which means that I write software that processes audio, and I also teach others how to write such software. I've created the dualsound.com blog and the associated YouTube channel. I also host a podcast, which is called Wolf Talk, where I interview researchers and developers from the audio industry. And I'm also, as part of my teaching endeavors, an online course creator. And in particular, I created a course called DSP Pro on the basics of digital signal processing for audio programming. And most recently, with the JUCE team, I created the official JUCE C++ Framework audio plugin development course. I'm also available for programming projects, training, and one-on-one coaching. So when you come to this workshop preview, I make a few assumptions about you. First one is that I assume that you know basic C++ and you are able to write a basic object-oriented C++ program. I also assume that you know at least what CMake is and how to invoke it. However, in the workshop or in the session, I don't expect you to write any or much of CMake list.txt files. And finally, I assume that you are interested in music in one of its various forms. From my workshop, but also from this preview, you will learn how to represent sound on a computer, how to playback sound in a cross-platform way in C++, how to playback an audio file, for example, for your video game, how to research, develop, and apply an audio effect to your sound, how to create a cross-platform audio plugin with a user interface for a digital audio workstation, and what all of these words mean will become clear after this workshop preview. You also learn how modern audio apps work, what not to do when you're processing audio with C++, and how audio programming differs from regular C++ programming. Finally, of course, if you're interested to learn more, I'll also provide information on this. So to those people who are on Zoom, please, you can interrupt me by asking questions in the Q&A. I have the Q&A list open here on the side. And this is particularly important because, I come here for the domain of audio in my mind. But I don't know how advanced in audio you are, and you have the right to be completely not advanced in audio, and that's my job to make you comfortable. So if there's a notion that I mentioned that's not clear or jargon, please put it in the Q&A, and I'll be happy to answer it in the middle of this session. We have plenty time for this. Okay. So as programmers, where can we find work when dealing with audio processing? Well, one example is right now, right? Because when I'm speaking to this microphone, there's a whole lot of software that's processing it so that it gets streamed right to your computer. The same case goes for video games. I mean, I don't know about you, but I could not imagine a video game without sound. Moreover, I'm also a musician as my hobby, and musicians in the world generally need a lot of software to compose music, to record music, to produce music, and also to playback music during concerts. Our smartphones, microphones, speakers, headphones, they all have a lot of processing on them. For example, I'm sure you've seen or tested noise canceling headphones. That's sound processing right there. And I just wanted to mention here another example is the speech business, right? There's a lot of work in automatic speech recognition so that we can talk to the computer and it understands what we're saying, but also text to speech, right? When the computer talks back to us with a given text. But these are just examples. There are many more applications of audio. So let's assume the simple scenario. We want to play back sound. How to do that in C++? Well, to answer this question, we first need to consider what is sound. Well, what is sound? Well, an acoustician would say that it's a propagation of periodic pressure changes in a medium, such as the air. But we can think of it that when a sound wave is traveling through the air, a group of particles hits another group of particles, which hits another group of particles, and so on and so forth. Actually, these particles oscillate back and forth. And this creates changes in density. This creates changes in pressure in the air. And that's what our ear perceives as the sensation of sound. But, this definition is only good for physicists, right? So we need to get the sound, the acoustic wave, into the computer. So how can we do this? For this, we need a device that's called a transducer, right? It takes a signal, an acoustic wave in one domain, and it transforms it into a signal in a different domain. In this case, it's simply a microphone. So it takes an acoustic wave and it outputs a voltage. Okay, and this voltage is this continuous time signal. But then we need to get it to our random access memory in our computers. So we need yet another device that's called an analog to digital converter, an ADC. And as a result, we get sound representation in our RAM. But what does the ADC do? Well, when we have our continuous signal, the ADC takes samples of the value of this signal at regular time intervals. This is called sampling. And these samples are discrete values that we can store on a computer, just like in a stud vector of floats that can be used to represent sound. It must be said that the distance in time between two successive samples is the sampling period in seconds. And its inverse is the sampling rate in hertz. And the sampling rate is an important number. It tells us how many samples constitute 1 second of audio. Okay, we have sound in our computer. But now we want to play it back. So we need to reverse the process of sampling. And for this, we need a digital to analog converter, a DAC. And what a DAC does, it takes vector of samples and the sample rates that they're at and converts it to an analog signal, to a continuous time signal. In this case, voltage. And this voltage can get amplified and put through speakers, and the movement of the speaker membrane causes the displacement of particles and causes the sound wave to propagate. So now you can see the full chain of how this works. Well, what is this magical box, this ADC and this DAC? It can look like this. And actually, it's something that I have on my desk right now. This is an external sound card. It's also called an audio interface. And actually, all our computers have an ADC and a DAC. You just need to look for a headphone jack for your headphones. It definitely has a DAC that, out of the samples that are in your computer, outputs a signal that goes through your headphones. And the same goes for your microphone, right? Most computers nowadays, most laptops have a microphone, and for sure there must be an ADC that records, that takes in this signal and changes it into samples. Okay, we know what is sound, how to play it back using C++. Well, the problem is that there's nothing like stud audio. Actually, there was a proposal for stud audio, but to my knowledge, it never got submitted. And who knows if it will ever will. So we need to rely on operating system specific APIs. For example, on macOS, we can use Core Audio. On Windows, we can use Direct Sound, and on Linux, we can use Alpha. If it sounds confusing, it is, because playing back sound in a cross-platform way already requires us to use 3 APIs, right? And if we want to abstract it out, it's quite difficult to do. So isn't there a library that already does this for us? And it turns out that there are quite a few. For example, there's Port Audio that we'll learn in this preview. There's JUCE that we'll also learn in this preview. But there are probably many others that I don't even know of. So let's look at some code. What if you want to play back sound using Port Audio? Well, this is a C-style library. So we need to initialize this by calling PA initialize first. Of course, when we're done with it, we should call PA terminate. And since this has to be called always when PA initialize is called, we can wrap it in an RAII style class. But the important bit comes next. When we initialize this library, we must call PA open default stream. And as you can see, it gets quite complicated, right? We see a lot of parameters here. So let's break it down. Here's the signature of the same function, PA open default stream. So the first argument, is a handle to a stream. If you're well-versed with C APIs, that's how we have how we can have an in-out parameter, right? So the open default stream will modify the stream pointer. So let's look at the remaining parameters. And the first ones that come up are channels, input channels and output channels. How many of them? Well, we said that one microphone results in one signal that gets converted into one array of samples. But what we have, if we have two microphones, we have then two arrays of samples. And these constitute two channels, right? So one microphone outputs a single channel of audio. But when we have speakers, or when we have headphones, we typically have two channels of audio. That's why you call it stereo. So in my example here, I said that I don't want any input channels. I don't want to record audio, but I want to have two output channels for stereo. Okay. Next argument is a sample format. The sample format is how we represent each sample value in our memory. And in audio programming, there's typically a float or a double in the -1 to 1 range. We assume that it's in this range, and it would stay in this range. And in Port Audio Library, we can do this using PA float 32 constant. Also, sometimes we use integer types, but I've mostly seen this used only when dealing with audio files, basically, not in actual apps or plugins. Okay, so the next argument we must pass to Port Audio is the frames per buffer argument. What is it? Well, first, let's consider what is an audio buffer. When we're processing audio, we typically do it in chunks of samples. And we typically do it with fixed lengths of such chunks. And the length of such a chunk is called the buffer size. So we could say that it represents a specific portion of time of audio to be played back. So for example, if we have 48,000 hertz sample rate, and we have a buffer that represents 10 milliseconds, our buffer size will be 480. Here you can see that the buffer can hold multiple channels of audio, and each channel should be of the length that's equal to the buffer size. So this immediately raises the need for the notion of a sample for each channel of audio. And this notion is called a frame. So we could think of a frame as a vertical slice through all the channels at a single time point. And so when we give a buffer size, we typically say how many frames there are in the buffer, or in other words, how many samples per channel there are. For example, when we have 480 stereo frames in the buffer, this means we have 480 samples in each of the two channels, which means we have 960 samples. All right, we're left with the last argument, the stream callback. What is the stream callback? Well, in Port Audio, it's a C-style function pointer. And Port Audio requires this function to have this signature. So it's already quite complicated. We have some input, output, we have frame count, which you already know what it is, and some other arguments. So actually what it is the function where the actual audio processing takes place. So we say to Port Audio, or rather to the audio device via Port Audio, hey, this is the function where I want to process audio. Please call it many times per second because I want to process audio there. And I'll give you the samples that you should play back via speakers. And the audio device will call it many times per second because we said that these buffers are quite short most of the time. And moreover, it is required that this callback is called on a real-time high-priority thread called the audio thread. So the audio device will call the audio callback on a high-priority thread, but it also in return requires that the audio callback returns within a prescribed deadline. Why? Because think about it. If audio device at a consistent rate requests samples from us, but we fail to deliver the samples, it won't have any sample to play back. So what it will do? It will glitch, which is a horrible user experience. And that's why we call it a real-time constraint. Okay, that's quite complicated just to start playback samples. Let's try to generate a sine signal. In digital signal processing, a sine is a very nice test signal. So when you think of a sine that's physically interpretable, you would think of this formula. In this formula for a sine, we have time, t in seconds. We have s of t as the output signal, f as a frequency in hertz, a as a unitless amplitude, and pi is a mathematical constant. So what this says, that if we want to generate a sine at the frequency f, we need to multiply f by 2 pi, and for each time point, multiply this argument by t, and then calculate the sine function of it. This is nice, but this is not very practical, because as we said, we want to generate samples. So we need to convert it to a discrete signal. We basically here convert the time to the sample index divided by the sample rate. The remaining arguments are the same, and the result are discrete samples of the sine that we want to output at a given frequency f. In reality, or in practice, what you'll soon discover, we don't even need to keep track of this argument n. So in the C++ code, it would look something like this. We have our amplitude, and instead of multiplying all these values together inside, we simply keep track of the phase of the sine. Phase is the argument of the sine function. And with each subsequent sample, this n increases by 1. So instead of keeping track of n, of the sample index, we can simply increment phase by the remaining multipliers of this argument. So we multiply by 2 times pi times the frequency divided by the sample rate. Okay, and here in the middle, we output the sample. Okay, how do we output the sample? Well, you remember in our audio callback, we get the output argument. What is the output argument? It's void star. That's a C way of saying it can be anything. But as you remember, we requested floating point numbers to represent our samples. So this will be an array of floats. But how can this be an array of floats when we have a buffer with 2 channels? So wouldn't we expect, something like this? That audio buffer shouldn't be, an array of arrays. We have a separate array for each of the buffers. Well, in reality, a lot of audio APIs, they give you a buffer in a so-called interleaved form. So instead of an array of arrays, we have a single array where the samples are interleaved. So the first sample in this array is the first sample of the first channel. The second sample in this array is the first sample of the second channel. The third sample in this array is the second sample of the first channel. And the fourth sample in this array is the second sample of the second channel, and so on. So instead of 2 arrays of, in this case, size 480, we have 1 array of size 960. But to be honest, we could process audio in this way, but it results in a not very nice looking code. But what we can do to help us is we can use a neat C++23 class called mdspan. I don't know, I'm sure you've seen span somewhere, MD-span is more popular, I think, among the research environments. But what an MD-span is, it's a non-owning view on an array. So the output that we got is an owning view, right? It's a C array that contains the samples. But now we use MD-span to look into this array, but in a little bit different way. So instead of doing index magic, we can just use MD-span, and it will simplify our code a lot. So we define a type here for simplicity called audio buffer, and it will hold floats. And it will have two dynamic dimensions. So the first dimension is the number of channels, and the second dimension is the number of frames. And these both need to be runtime dimensions, so-called extents, because we don't know at compile time how many channels we'll have or how many samples we'll get in each buffer. And the last argument here is the layout. And we specify the layout to be layout left, which corresponds to MATLAB-style programming, but it will make it much easier to access the samples in this way. And to create our audio buffer, this view into the array, we convert the output array to a C-style float array, and we say, okay, this has 2 channels and 480 frames. Here I gave constants, but you can imagine that these will be variables in production code. Okay, and as a result, we can access our buffer in this beautiful manner. We can index it by channel and by frame. So we have our array of arrays. So in this code, what we do once again, we iterate over all frames in the buffer. So you can see extent 1 is the number of frames. We generate the sign sample, and we output it to all the channels. And as you remember, the number of channels is given by the first extent. And then we increment the phase as before. And this will sound something like this. But before I play it back, a word of warning. So it hasn't happened to me yet, but I've heard from quite a few audio developers that they actually got hearing loss, partial hearing loss, of course, because they were testing their audio software in headphones. Remember that your audio software is also prone to bugs and glitches, so you should never test it using headphones unless you want to risk your hearing. So, okay, so let's listen to the sign. I hope you're able to hear it. Okay, so that's the amazing result that we got out of playing back a sign. And when we're done, we need to clean up in port audio. So we need to stop the stream when we're done playing, and when we don't want to use it anymore, we just call close stream. And again, we can wrap it in a nice array.ii class with nice start and stop functions. Okay, let's summarize. What do we need to do when we start playing back audio in C++? Well, we need to connect to the audio device on our operating system. We need to give it the audio callback. So we need to say, hey, this is the function that we'll use for audio processing. And then we say, hey, please start calling our audio callback. And the audio device will say, okay, and start calling our audio callback at a fixed rate. In our audio callback, we need to consume or produce the samples regarding of our application. And when we're done, or the user presses the stop button, we can stop the playback. And finally, we need to close the connection to the audio device. And all this will be covered in the workshop. You'll be writing code that does all of these steps. Okay, this is a good point. If you have any questions, please put them in the Q&A, and I'll be happy to answer, because this was an important part. Okay, let's consider, why is C++ good for audio? Why people still use C++, not something else? Well, as attendees of C++ Online, you know that C++ is great for high-level but zero-cost abstractions. But you may say, okay, we have Rust, right? Why cannot we use Rust for audio? And a lot of companies are using Rust. But C++ has this amazingly easy C and Objective-C interoperability. And this is important for a few reasons. Well, first, operating system audio APIs are sometimes written in C, or even better for us, they're written in C++, for example, for Windows or Android. So you can imagine that for Rust, for example, we would need to create this whole intermediate layer of translating into C. But the most important argument, I believe, that C++ is so popular for audio is that it has amazingly powerful C and C++ libraries and frameworks related to audio, such as FFmpeg, a big library for processing audio and video, or the JUCE C++ framework. Okay. Someone commented, the header that you used is open source or proprietary. Port audio is open source, and the remaining stuff that I used is open source. And it's easy to check their license, but to my knowledge, like JUCE is open source, but if you want to release a commercial application, you need to have a license. But for personal use, it's completely free. And AudioFiles is MIT. And Port Audio has also a very permissive license, if I remember correctly. Okay. Next, we know how to play back sound. How can we play back an audio file? And we mentioned the audio file library. We can simply use it. And that's quite easy. We define a file path. We instantiate the audio file object. We load the file, and we keep track of where we are in the file so that we know that we don't try to play back more samples that there is in the file. And then in the audio callback, we limit ourselves to the number of channels in the buffer or in the file, whichever is smaller, and then keep track of our position in the file and output all the channels that we are able to the buffer. This is super easy. And this is the result. Okay, amazing. But one important thing that we can note here is that we didn't read the file in the audio callback. And why cannot we just read the file in the audio callback? You can imagine that for a music player application, this would be very handy, right? And actually, we cannot do this. As we said, our audio callback must complete within a time limit. That's what we call real-time programming. And the problem, of course, when we miss it, we get a glitch. But the problem with the file input and output is that these are all system calls, and as such have unbounded execution time. And if you've ever benchmarked any file input-output code, you know how slow it is. So we would definitely get a glitch if we would try to read from a file in the audio callback. But in the same vein, in the audio callback, we cannot allocate or deallocate memory, which makes our code very complicated to write. We cannot do this because these are system calls. The same way we cannot do networking calls. These are also system calls. We cannot take a lock on a mutex. This is also a system call, but if you think about it, it creates the risk of priority inversion. Our audio thread is high priority thread, but if it waits for a mutex that's locked, it will need to wait for a lower priority thread, and we may get a glitch. Similarly, we cannot start threads, we cannot wait for threads, because it is either a system call or it has unbounded execution time. And similarly, we cannot call any functions with unbounded execution time. And there are many more rules that we must follow in audio processing. So that's a big part of audio programming complexity, is that how little we can do on the audio processing thread. And I know firsthand because I've made some of these mistakes myself. So that's why we have this workshop, so that you don't have to do this. Okay, we have a music player. Now we'd like to apply an effect to it. How can we go about it? Well, the area of audio effects is a subfield of digital audio signal processing. And if you think about it, programming and digital signal processing, maybe I should say real-time audio programming and digital signal processing overlap in this tiny bit in the audio callback. That's where we can implement signal processing algorithms. So let's look at an example effect, a flanger. Here's how it sounds. Okay, as you can see, it is a effect that changes over time. It is a dynamic effect. Okay, so this has been around since 1960s, I believe, but now we can implement it in our software. But how? Well, this is something that we'll delve to in more detail in the workshop. But essentially what we must do, we must scout the literature. We must look through textbooks and through research papers to see if there is an algorithm that fits our needs. Of course, if you want to do something truly novel, you need to come up with such an algorithm yourself. But for the most part, a lot of those algorithms have already been published. Okay, so we plow through the research literature and we see something like this. And this is where a lot of people get scared, right? Because, okay, this is a diagram, but what does this represent? What does this mean? And as someone who creates audio plugins or audio effects and implements them, you need to be able to read and understand such diagrams. So let's break it down. Well, first, on the left-hand side, we have x of n, which is the input signal. And you can think of it as single samples coming one in at a time. On the right-hand side, we have the output signal. So whenever we get an input sample to our effect, we need to produce one output sample. Then here in the middle, we have x h of n. And this is a helper signal. So this isn't an additional signal that we have here. It's just a notation that I introduced, so it's easier to reason about this effect. You can think of it as a helper variable. D here and here is the length of the delay line. And what is a delay line? I will explain in a bit. Then we have three coefficients, blend, feed-forward, and feedback, that simply multiply the samples that go through them. These are simple constants. Then we have this SLFO unipolar signal. What is it will become clear soon, but let me just tell you, it's a generator. So inside our effect, we have a sine generator that we use to make the sound more dynamic in the effect. And here M is a so-called modulated tap. So this is a delay that delays our signal, right? And this delay changes here. I'll explain it all in a moment. And finally, we have another delayed signal that goes from the middle of this delay into the feedback loop. Okay, what do these words mean at all? So first, the LFO. An LFO generator is a low-frequency oscillator. What it means is that we generate a signal in our effect that hasn't come from the input samples. We generate it ourselves so that we can make our audio processing more interesting, more dynamic. That's what we heard in the flanger effect, that it changed periodically, and that's thanks to the LFO. And here I just marked the difference between bipolar and unipolar LFO, and in flanger we use a unipolar LFO. But then comes the more difficult bit, the delay line. I remember in one of my workshop, there was a great software engineer that came and said, okay, but what is a delay line, right? And this is very natural, and you don't need to understand it. That's what the workshop is about. But nevertheless, I'll explain it here. So the delay sits here in the middle and is a very important part of the flanger effect. And what it does, it simply delays the sample by the number that we have here. Like this is just a DSP notation. It says delay by 5 samples here, for example. And in plain words, we could say that the output sample is equal to the input sample from 5 samples ago. And we typically denote it like this: y of n equals x of n minus 5. But as programmers, we can look at the delay like this. So it actually lengthens the path that the signal takes through our effect. So let's take a look how it operates. Initially, a delay line is a simple vector or an array filled with zeros. Whenever the first sample comes along, it wants to enter this buffer, but there isn't any place here. So the elements need to shift to the right, and naturally the last one pops out, and it's the first output sample. So as I said, we have one input sample, we must produce one output sample, and that's what happens here. Okay, but then another input sample comes to our delay line. So again, all these elements must shift to the right. And so another 0 pops out, and we have another output sample. And we repeat that until all the zeros have been popped out. So what happens now? All the elements shift to the right because x of 5, the sixth sample, want to move out. And so we produce the sixth sample of the output, which is the first sample that we put in. And you can see already, so that the sixth output sample is the first input sample. So we effectively delayed the signal by these 5 elements, by 5. And this goes on and on, right? As long as we input samples, we'll get output samples. And we can denote it like this. And you can see that the output is always the input signal delayed by 5 samples. So if you look at actual audio signals, it looks like this. Let's focus on the top one first. Here we have a sine signal, which has 5 samples per period, right? That's the period. And we delay it by 5, so by full period. So you can see that at the output, the blue signal here, we get a copy of the signal essentially shifted by 5 samples. And if we add now the input signal and the output signal, they will be reinforced, right? Because they were delayed by the period, so it's actually identical apart from these 5 zeros. But let's look at the signal, input signal. It has a period of length 10 samples. If we delay it by 5, so half of its period, we'll see that the blue output signal has exactly opposite values to the input signal. So if we now add the input and output signal, they will cancel each other out. And that's the principle that lies under the flanger. Some frequencies are boosted and some are suppressed. And thanks to the LFO, it changes over time. All right. So we understand the discrete bits here, right? Here the delay line is modulated, and the amount of delay changes with each sample. The delay tab here, this d/2, is fixed. And, you know, when we implement this stuff, as just a side note, I showed you, pushing out samples, but we typically implement it as a circular buffer, if you're familiar with this term. But don't worry, in the workshop, we'll use a ready-made delayed implementation, unless, of course, you want to implement your own. Okay, we have this diagram, but to implement this in our audio processing, we need to bring it to a different form, a form of so-called difference equations. Now, how do we go from the block diagram to difference equations? And that's something that a lot of students struggle. And we actually analyze this in detail in the workshop. But the general principle is this. Look at the output and trace it back, right? So we have our y of n, and what does it equal to? It equals to an addition of feed forward times xh of n minus m, and the multiplication of blend times xh of n. And that's it. We can write it down. y of n equals blend times xh of n. That's what we have here. And plus feed forward times xh of n minus m. So this one here. Okay, but now what is xh of n? Let's trace it back. It's a sum of x of n plus feedback times xh of n minus d divided by 2. So this fixed delay. And we can write it like this. And this is okay. You may think that we define xh in terms of xh, but actually these are past samples, so we already know them. So we calculate the current value of xh using one of the previous values of xh. And finally, we need to also know what's the delay, current delay that this xh of n minus m is delayed by. So once again, this LFO changes the delay that we get these samples out, this xh of n minus m. So we need to calculate the delay value for the current sample. And note that I wrote here 3, 2, 1. That's how we derive these difference equations. But now when we implement this, we go the other way around. So for each input sample, we say, hey, what's the delay length? We calculate it using the LFO value and the delay length. Then we calculate the helper sample and then the output sample. And the amazing thing is that it's really easy now to put it into working code. So that's how such a class would look. But for this presentation, it's important to just look at the process sample function. Okay? What do we do here? We actually implement just these equations. So let's start with this one, modulated delay value. How can we do this? Well, we have the LFO sample here, and we calculate the unipolar value of it, and then multiply the length of the delay, the maximum delay, and so we get the current delay. This is our m. Okay, what's the next part? We calculate the helper variable. xh equals x. Okay, we have xh equals x plus feedback times xh of n minus d divided over 2. So that's what we have here. Feedback times delay line of the middle delay, right? Because this middle delay is in the middle of our delay line. And finally, we calculate the output sample. Blend times xh, that's what we have here. And feed forward times xh of n minus m. And that's where we use the current delay value to pop the sample. Before we return the output sample, we need to update the delay line. We need to push, as we saw here, the helper signal here goes into the delay line. That's what pushes the samples forward. Okay? So we push the sample and return. And that's it. That's basically the whole implementation. Okay, are there any questions pending? Okay, I assume not. Okay. Let's look at what we have so far. We have a sign generator, we have a file player, we have a flanger, and they more or less have the same interface, right? I'm stretching it a little bit, but you know what I mean. So they need to be prepared somehow, right? Above all, the sign generator needs to know what the sample rate is, and the flanger needs to know what the sample rate is. And then we just process it. And actually, it's not a coincidence, because that's how most audio processors are defined. We need to prepare them, and then we can process the audio buffer. And that's actually what you'll see in the JUCE C++ framework. This allows us to chain processors. So we can have an entire chain of processors that all process audio. But actually, if you think about it, we had one file, and we put an effect on it. So we had two processors. But now, allow many files to be processed in parallel by many different effects, and you get a digital audio workstation. So what you can see here is that we have multiple channels. Each one has some data on it. It could be an audio file, it could be a MIDI file. And then when we play back, the audio files just play back, and the MIDI file gets converted by a sound synthesizer effect into actual sound, and then we can put effects onto it. And that's actually a very big work of field, working on such DAWs and working on the effects of these DAWs. So for people who are in this field, they understand how this works. But for people who do only C++ development, it's important to explain how this works. So let's look at this diagram. Our digital audio workstation is on the left side, right? It's an application. It may have its own effects, but it also is a plugin host. It can use effects provided by the users. Whichever effects I install on my machine are available in the DAW. So the user may provide many additional effects. And that works great because we have a big market for DAWs and a big market for plugins. And that's how it looks. We have a plugin host that communicates with a plugin via a plugin API. And there are a few plugin APIs, but both the DAW and the plugin must conform to it so that the communication is successful. And how does it look currently? Well, Apple has their own Audio Unit v3. What's interesting, it also works on iOS. Steinberg has Virtual Studio Technology 3 that's widely supported among many DAWs. Then there's the AX format, which is only available for the Pro Tools digital audio workstation. Linux has its own format. And then the most recent addition to the plugin APIs is the Clever Audio plugin format. And if you think about it, it's a real development nightmare, right? Because we just want to produce one effect that works in all DAWs, but now we need to support all these plugin APIs. And let me tell you, it's not easy to conform to them. Like the documentation of VST3 has loads and loads of pages that you need to understand to do it right. So naturally, plugin frameworks emerged. These are tools that abstract out the APIs of particular plugins, and so we can develop our effect once, but have it built for various plugins. And the biggest and most popular one of them is the JUCE C++ framework. Apart from this functionality is a general-purpose cross-platform application development framework. You can think of it like Qt if you know it. It's easy to develop audio plugins and plugin hosts with JUCE. Literally specifying a new audio plugin format is adding one argument to a CMake function call. JUCE has many related audio features, so it makes it easy to build audio effects synthesis, handle MIDI, interact with the audio device just like we did with port audio, read audio files just like we did with audiophile. And let me just note that we recently released an official JUCE audio plugin development course, which is entirely free if you want to check it out. But actually in the course, we'll focus on the crossings of this domain. So not just JUCE, but also understanding how audio effects work, and we'll actually and how to do the research and then derive the design to implement the plugin. And this is the prototype UI of the plugin that we'll implement, which I believe is a good example of not so easy DSP, so quite an advanced audio effect, and some user interface on top with plugin parameters with some extra features. So from this workshop, you will learn, once again, how to represent sound on the computer, how to playback sound in a cross-platform way, how to play an audio file, how to apply an audio effect to your sound, how to create a cross-platform audio plugin with the user interface for a digital audio workstation, and we actually test the plugin out in a digital audio workstation. And you'll learn how modern audio apps work, what to avoid on the audio thread, and you'll get a feeling, a hands-on feeling, how audio programming differs from regular C++ programming. If you want to take it further to create your personal projects, or as many developers you want to transition to audio programming, I'll also tell you where you can find more information. The outline of the workshop is very simple. First, we'll start by compiling the code, which is often the most important bit, but luckily you will have a good internet connection. Then we'll proceed with just a minimal introduction to audio because I want you to start writing code as soon as possible to playback sound. Then you'll modify the playback sound by using audio effects. We'll take a small break, and then we'll build a full-fledged audio app and plugin with a user interface using the JUCE C++ framework. Finally, we'll wrap up, and I'll list you additional resources if you are curious. What I expect of you in the workshop is, as I said, basic C++ knowledge, understanding of basic CMake commands. You need to have CMake Git and the C++ compiler and build system installed. And please, if you have older versions, please update to the latest possible, ideally to ones that support C++23. Then please install the Reaper Digital Audio Workstation because it's, I think, best for developers to check out their plugins. And also there's a very nice trial version. And if you're a Linux user, please install the necessary Linux packages as JUCE tells you to. Here are the time slots that my workshop is available. Here's the link you can register with. And the word of summary, remember that audio is processed in samples at a sample rate in the callback of the audio device. The audio callback code must be real-time safe, so we must complete the audio processing within the deadline. Remember that still C++ is the most popular language for real-time audio processing. There are alternatives, but none of them has overtaken C++ yet. And finally, that the digital signal processing is the theory of audio-related algorithms. Thank you so much for your attention. That will be all for the live stream. And now I'll proceed to Gathertown